This video is on laminar flow and viscosity. It's an example problem where we will look at the velocity profile of a river. And it is basically taken from the lecture notes of Professor Michael Fowler, and you can find these on the internet if you just search for Michael Fowler fluids. So let us consider a river of depth h flowing down a slope of angle theta at a steady rate, right? So it's not accelerating. And what we're going to do is set up our coordinate axes, perpendicular and parallel to the surface. We are also going to divide this river into several layers, and we're assuming that this is in the regime of laminar flow, so these layers don't really mix all that much, and each layer is a thickness dz. And for ease of reference, I've labeled 3 of the layers, so we have 1, 2, and 3. We're mostly going to be focusing on layer 2. So our system is going to be a thin layer of water, or any liquid you like, in particular layer 2. It's going to have some density rho, it's going to have a thickness dz, it's going to have an area of contact A, right? So this area, remember it's being shown in cross section, so this area of contact between the 2 layers is A. And similarly between layer 2 and 3, that area is also A. As always, when dealing with a force problem, we draw a free body diagram. So here we will draw a free body diagram of layer 2. So once again, here's the situation. The river has a total depth of h. We're going to set z equals 0 at the river bed, and we're going to say that the bottom of layer 2 is at a distance z, and then the layer 2 itself has a thickness dz. So this interface is at z, and this is at z plus dz. Remember, acceleration is 0. So the forces on layer 2, we have the weight of the layer, which will be the gravitational force mg. We have the normal force of layer 1 on layer 2. It will be pointing perpendicular to the surface. We have a normal force of layer 3 on layer 2. It will be pointing perpendicular to the surface and downward. We have the viscous force. So it's V for viscosity, not for velocity. So the viscous force of layer 3 on layer 2 is pointing forward, because this layer is traveling fairly fast. This layer is traveling, well, this layer is trying to be still, this layer is slow. So layer 1 will try to slow down layer 2, layer 3 will try to speed up layer 2. So the viscous force of 3 on 2 is pointing forward, trying to speed it up. The viscous force of layer 1 on layer 2 is pointing in the opposite direction, trying to slow it down. And what we're looking at is the steady flow situation where all these forces will balance out and we have a net acceleration of 0. Now that we have the free body diagram, we can write our equations, second law equations, in the x and z direction. So let's start with the z direction. We have F net z equals maz, and in the z direction we have the normal force of 1 on 2, we have the normal force of 3 on 2, the negative z direction, and we have a component of the force of gravity, and we can see that this angle is also theta, the same as the slope angle there. And so we have minus mg cosine theta, and all these components put together give us 0 in the z direction because there's no acceleration. And similarly in the x direction we have the viscous force of 3 on 2 in the positive x direction. We have a component of gravity which is also trying to speed it up, mg sine theta. And we have the viscous force of 1 on 2 in the opposite direction, and again all of these x components added up equals 0 because this is steady flow, so there is no acceleration. So let us focus on the z direction first. So the equation we had was this, and what we're going to do is rewrite it. So the normal force is really caused by the pressure. And the normal force of 1 on 2, well, that interface of layer 1 and layer 2 was at position z along the z-axis, So it would be the pressure at the position Z times the area of the interface. So I've put these little red brackets to indicate this is P evaluated at Z, not P times Z. Similarly, we have the normal force of layer 3 on layer 2, and that interface was at position Z plus dZ. So what we have is the pressure evaluated at Z plus dZ and then times the area. And this one was pointing downward in the negative Z direction, so we have the minus sign there. We want the mass of layer 2. So the mass of layer 2 would be its density rho times the volume of the layer. And the volume of the layer is simply going to be the area times the thickness dz. And then the g cosine theta just carries over. So all of this together is equal to 0. So just for clarity, I folded the paper so you can see the diagram and relate it to the equation that we got. And so we see that, yes, the interface of layers 1 and 2 was at distance z. So we had pressure evaluated at z. Similarly, the normal force of 3 on 2, which was pointing downward, that was happening at a position of z plus dz. So that's why the pressure evaluated at z plus dz is what we had. And also the volume, when we were calculating the volume of layer 2, that was the area times dz. So it was the area of this interface and then times the thickness dz. And that gave us the volume. So proceeding from this equation, what we do is we rearrange things. So we notice that we have this pressure evaluated at 2 different positions. So we're going to isolate that. We have a common factor of a for all 3 terms. So we're just going to divide through by a, and it's 0 on this side, so there's no change on this side. And then we'll move these 2 terms to the other side so that we have p at z plus dz minus p at z is equal to what remains here, so that's minus rho g dz cosine theta. And then what we can do is we can divide this dz over. So we have p evaluated at z plus dz minus p at z divided by dz is equal to minus rho g cosine theta. But we have seen this structure before. A function evaluated at 2 different points which are separated by an infinitesimal distance, and then we divide that difference by that infinitesimal distance and take the limit as dz goes to 0. But this just becomes a derivative then. So it becomes dp over dz. So we have dp over dz is equal to minus rho g cosine theta. So what we have achieved is a differential equation for p as a function of z. And this is a straightforward equation. We can integrate it to find the pressure. So we integrate it. All these terms are constant. So we just get minus rho z g cosine theta and then plus a constant, which we'll call c1. We would like to fix that constant. So we notice that when we are at the top surface, when z is equal to h, then we're at the top of the river, and so the pressure is just equal to the atmospheric pressure. So when z is equal to h, we have minus rho g h cosine theta plus c1, but this must be equal to p atmosphere. And so c1 is just equal to p atmosphere plus rho g h cosine theta. With that in mind, we can plug back in for c1, and we get our full function for p as a function of z is p atmosphere plus this quantity rho g cosine theta brackets, so in this case times h minus z. And this was in the range z between 0 and h, so in the river. And we see that this expression makes physical sense. We see that when z is equal to h, it's just the atmospheric pressure. But when z is less than h, when we're inside the river, we have some additional pressure. It's not just atmospheric pressure. We have a contribution due to the liquid, and it depends on the density of the liquid. It depends upon how deep inside the river you are. Now that we've had some practice in the z direction, let us continue and look in the x direction. Newton's second law applied to the x direction gave us this equation. So let's see what substitutions we can make. The viscous force we know is proportional to the area of contact, the coefficient of viscosity, and the velocity gradient. This is the viscous force of layer 3 on layer 2. So this velocity gradient, which changes with position, must be evaluated at z plus dz. Similarly, the viscous force of 1 on 2, again we have the area of contact, we have the coefficient of viscosity, and we have the velocity gradient evaluated at position z. Finally, we have the mg sine theta term, and again we replace the mass with the density times the volume of the layer, which is adz. Once again, we notice that we have a function which is evaluated at two different positions. So we isolate those terms. Again, we have a as a common term for all three terms. So we can pull it out and divide it over. Well, we just have 0 here, so it goes away. We've gotten rid of a. We move this term to the other side, and then we're left with just these two terms. We see that eta is common to these two terms, so we extract that and divide it over. And so we are left with the difference between these two velocity gradients is equal to minus rho a dz g sine theta over a eta, and the a's anyhow are going to cancel out, and so we can divide the dz over, and we are left with this expression, which again has a similar form. We have a function evaluated at z plus dz minus the function evaluated at z divided by dz, and it's equal to this expression over here. Once again, we will take the limit as dz goes to 0. So here the function was already dv over dz, and now we're taking the derivative again with respect to z. So what we really have is d by dz of dv over dz, but that's the second derivative of the velocity with respect to z. So we have d squared v over dz squared is equal to minus rho g sine theta over eta. We integrate once, we go from the second derivative back to the first derivative. We pick up a z over here and a constant of integration, we'll call that c2, and then we can integrate one more time. And so we have v as a function of z is minus rho g sine theta z squared over 2 eta plus c2z plus c3. All right, so we have found the velocity of the water as a function of z. But we have two constants, so let's see what we can say about them. Well, we know that at z equals 0, well, that's at the riverbed, we expect that since the riverbed is stationary, the water right next to it should be stationary as well, so the velocity should be 0. So we can set, z equals 0, this term will go away, this term will go away, so we're left with just c3, but that should be 0 as well. So that fixes c3 for us. But we're still left with c2. Well, going back, notice that this was an equation, differential equation with a second order derivative. How do we constrain c2? A second order derivative means we need two pieces of information. So just like how in mechanics we would have seen equations for acceleration, which is the second order derivative of x with respect to time, and to fully solve for the motion of the particle, we would need the initial position and the initial velocity. Similarly here, we should look at not only v, but the derivative of v with respect to z. Now there are two places where we could evaluate that. So we could evaluate v at z equals 0, and we could evaluate v at the top at h. We can evaluate dv over dz, the derivative, which is the velocity gradient, at z equals 0, and we could evaluate the velocity gradient at z equals h. So we need two pieces of information. We've already used v at z equals 0. So one of these three, as long as we get one of these three bits of information, that should be enough for us to fix what C2 is. This is a fairly common thing that comes up when solving differential equations for physical systems. We try to look at the boundary conditions of not only the function but its derivative. In this case, we are going to look at the derivative, the velocity gradient, at the top of the river at z equals h. What we notice is that for the topmost layer of fluid, that is layer 3, if we write Newton's second law for the layer 3 in the x direction, we notice that we have a gravitational term which is trying to speed it up, and we have a viscosity term which is trying to slow it down, and that's it. Because it is the topmost layer, there is only one viscosity term, not two. We can follow the same procedure as before and substitute for the mass in terms of rho adz, substitute for the viscous force. All right. But our previous trick of rewriting things to make them a derivative, it doesn't work here, because for that we need a function evaluated at two different positions separated by dz. Here we just have the velocity gradient at one position, z plus dz. Still, this is a true equation, and so it should hold no matter what value of dz we take. In particular, as in the limit as dz goes to 0, this equation should still hold. But in the limit as dz goes to 0, what do we get? We get dv over dz goes to 0, because if dz goes to 0, this term will just go away. So we get this term is equal to 0, and eta and a are constants and non-zero, so you can divide them over. So we get dv over dz evaluated at z, because the dz has gone to 0. So dv over dz will go to 0 at z equals h, because that is where the interface will be as dz goes to 0 for layer 3. So we write that as dv over dz evaluated at z equals h equals 0. So this is a boundary condition, and we can use that to fix C2. So going back to the velocity function, we already got rid of C3, so we're left with this. We take the derivative. As a function of z, it is this. We evaluate it at z equals h. So dv over dz evaluated at z equals h is minus rho g sine theta h divided by eta plus c2, and this should be equal to 0. We solve this for c2, and then we go back to the velocity function and plug in for c2, and this is now the full expression for the velocity as a function of z. And we can see we have some common factors, so let's pull those out. So we have rho g sine theta z over eta times h minus z over 2. So if we look at what our velocity function looks like, what we see is that, oh, at z equals 0, this will go to 0. So yes, the velocity is 0 at the bottom. And well, this is a quadratic function of z. So it's a parabola. The velocity profile is a parabola. It gets faster and faster as it gets to the top of the river. But it reaches exactly the midpoint of the parabola at the top. Right? So that's why the derivative goes to 0, that the gradient, velocity gradient goes to 0 right there. So yes, from simple physical considerations, we have determined what the velocity profile of a free-flowing river, steady-flowing river on a slope is. and we can use this to get further information. Supposing we wanted the flow rate, that is how much water actually passes by a certain point. So let's say we have a river of width W and a depth H, and it is flowing steadily. So to find the flow rate, that is what volume of water flows past a certain point, what we need to do is integrate the velocity times the width times dz, because well, we're basically trying to find the volume per unit time, and the velocity gives us length per unit time. So if we multiply it by the area of cross section, basically like that, then we'll be able to see how much water flows past it. Right, it's the flux through this surface. And so what we do is we multiply the velocity by the width w and by dz, and integrate z from 0 to h. So we plug in for the velocity, pull out all the constants we can. W is also constant, we pull that out, and so we integrate z, well, this function of z from 0 to h. And what we find is it simplifies very easily. It's just a polynomial, and we evaluate it at 0 and h, and so this is finally our flow rate. It's rho g w h cubed sine theta over 3 eta. All right, and we can check that this has the right units of volume per unit time. But also notice that this depends on h cubed, right? Only the first power of w, but on h cubed. And so if, for example, during a storm, the depth of the river simply doubles, right? If h doubles, the flow rate, the amount of water that is actually flowing past, will go up by a factor of 8. Right? So this is why, for example, even slowly flowing rivers can they carry a truly tremendous amount of water, and you should be careful, for example, of driving your car into even a slightly flooded street, because there's a tremendous flow of water and thus of momentum, which can affect your car. And this is the end of this example. We'll be proceeding in the next video to see how viscosity affects drag.